Okay. Hello, everybody. Thank you for joining us today. Today we're going to be talking about building payments infrastructure that scales. We're going to be going over a bunch of different stuff today, so I'll try to keep it concise, all the different sections. But we're going to be talking about tokenization, isolation, and API design. And in essence, we're going over a few of the different lessons that we've learned. We're going over a few of the different lessons that we've learned over the years at VGS. And a little introduction about me. My name is Travis Mottershead. I work at VGS running product delivery. I started coding when I was 17, and I'm incredibly passionate about software development. And I heard it said earlier today, the craft of software engineering, and I think that is a very apt way to describe it. It's a craft. It's something that we can become better at, and I love seeing how elegant software helps make life better for people. So, kicking it off, we're going to be talking about what is tokenization, how to deploy code that scales globally for global customers. We're going to be talking about what is business value, which is a bit of a pivot. We're going to be talking about both technically deploying infrastructure and also understanding what business value is, which informs how we design our APIs. So, by the end of this presentation, you should have learned how enterprise payment systems work, and it's a bit of a crash course that we'll be going over. You will have learned how to deploy software in a way that is fault tolerant as your customer base grows and diversifies. And we'll talk about how organizations value products and how slight changes in API design concepts can drastically simplify life for you and for your customers. So, what is tokenization? This is a crash course on enterprise payment systems, just to set the stage on what the nature of this all is. So, enterprise payment systems typically start out using a single payment processor, such as Stripe. And these processors will collect card details from the front end, and then that will go directly to the processor. And after the processor performs that transaction, they provide the merchant with a PSP token. That PSP token can be used for recurring payments, and it can be used to track the lifespan of that card. Now, as merchants evolve and as they grow, they often add multiple processors, both for redundancy, and then they can have different flexibility in their payment orchestration system. So in this case, the client is no longer using the payment processor's iframe directly. Instead, the client side uses the card details. If I'm just talking without VGS in the mix, it's going directly into the website. And so the client enters into a collect form, and those card details go to the merchant server. From there, the merchant can decide if they want to process that transaction with Stripe or with Adyen or with Braintree or with N number of other processors that are out there. Now let's talk about token definitions. There are two types of tokens that we're going to be diving into today. There are many types of tokens. It's a very utilized term in the industry. But data tokens represent a one-to-one mapping of a specific data element. So here we have the card number, which is 4111, just a sample card number. And then we can create a data token that represents that direct value. Likewise, we have the CVV of that same card, the 123, that gets a different tokenized value. And these data tokens can be used to securely share the original data with any third party, because you know that you are working on an exact representation of that data element. And they can be used on any type of data. So it does not have business context. So whether you're talking about PANs or CVCs or social security numbers or bank account numbers, a data token is one-to-one. A PSP token, on the other hand, this is what we were touching on before. This is a token that represents an entire card or other payment instrument. And this is often linked to, or this is inherently linked to one payment processor. So if Stripe issues you a PSP token, then you can perform payments with Stripe using that PSP token. Now, that PSP token does not represent the PAN directly. It represents the combination of the PAN, the expiry date, the CVV, the customer name. There is context along with the token. Now let's talk about payments using VGS secure data, just so that this is going to set the stage for us to understand what it means to scale globally. So VGS has two proxy services, the reverse proxy and the forward proxy. And we also have front-end collection services. So on the front end, the PAN and CVV are loaded into a VGS collect form. Obviously, this would be PAN, CVV, the expiration date, all of the information about that card. The data goes through, it's submitted, and as that raw data goes through the VGS proxy, we convert the raw PAN and CVV into a data token for the PAN and a data token for the CVV. That data gets forwarded over to the merchant server, where the merchant can decide, do I want to send it over to Stripe, Adyen, Braintree, or one of the n number of processors who they're using. And when that is done, the PSPs generate PSP tokens, so that those PSP tokens can be used for recurring payments. This is a very common enterprise payment architecture. And then, because VGS is operating based off the HTTPS protocol, it is very flexible because we are creating data level tokens. So when you ingest data through the reverse proxy, you can specify which fields you want to create tokens for. In a payments context, that's going to be PAN and CVV. But in other contexts, like in other contexts, and that could be other data elements. Because of the flexibility, the technology ended up being used by thousands of developers around the world, from merchants, fintechs, gateways, issuers, or marketplaces. These are some of the different customer segments that we're working with. And we have global brands who are operating, major banks. And then we also have early stage startups who are quickly trying to reach compliance. They just don't want to touch that data. They want it all to be tokenized before it touches their system. So how do we reconcile these two? How do we ensure quality of service to all customers who are using the system in all the different segments and from all the different sizes all over the world? And because of the diversity of use cases, we needed to ensure that one customer was not impacting any other. This is one of those lessons that you learn as you grow. So quickly, a customer story. Enterprise merchants with Black Friday sales. Typically, many merchants have a very static behavior throughout the year, and there's some seasons that have higher purchasing, but November, December, when those holidays come around, that's when we see a dramatic increase in the amount of sales. So this is Black Friday, Thanksgiving, Christmas, New Year's. This is when we start to see spiky traffic. In order to support these customers in a way that was the most safe, we developed a cell isolation architecture. This is an architectural strategy that will limit blast radius of any issues. So when something happens, if one of the customers was operating in an unexpected way, then it would be limited to just their environment. This is similar to a bulkhead on a ship, where a ship will be segmented into multiple bulkheads. So if one of the bulkheads get taken out, the rest of the ship does not is not impacted, and it can continue to sail. This is a fault-isolated, we have fault-isolated boundaries that restrict the effective failure within a workload to a limited number of components. That's a more technical way of describing this. So here is an example of the original architecture where we have our database layer and we have EKS or Kubernetes, and then we have our application layer on top, and all of the different customer tenants are sitting on top of that same application layer. With cell architecture, we have introduced this cell, you can see cell 1, 2, and 3, and now the applications are tied to that cell. So when we are hosting, those applications, we know that we are deploying it to one cell, and customer tenants will only use that one cell. These are Helm template instances deployed through GitOps, and each cell deploys to multiple AZs. What this means is that when a new customer comes up, like the story that I told before around that merchant who had exceptionally spiky traffic near the end of the year, we can move that customer quickly into their own environment, into their own cell, so that their traffic is not impacting anybody else's traffic, and then we can monitor it specifically. We can scale up resources as needed in a very controlled way. When we find more customers who are similar, who have similar behavior, we can move those customers again into the same cell. So we are logically grouping customer segments into these different cells. What this also means is that if we need physical isolation for one of our customers, we can spin up a new database layer, and we can tie one of those cells to that database. And as part of this, we have canary rollouts where we can start rolling out to cell 1 and then make sure that it scales up effectively, move over to cell 2, it'll scale up effectively, so on and so on. So here is another customer story where we have, VGS supports a global event streaming services. And with these services, people, this is typically sports events. People like sporting events all throughout the year. There are times of the year where certain leagues will have their time where everybody tunes in, but more or less everybody is interested. What we have found with this customer segment is they have exceptionally spiky traffic where 5 minutes before an event, all of their payments come through. Everybody signs up for the service. What this also means is these are global event streams. So somebody might be in Japan streaming an event that is happening in Europe, or somebody might be in the US streaming an event that's happening in Australia. And so there's a lot of different things that could be, traffic can be coming from all over the place, and there's a lot of things that could go wrong. So VGS, in order to solve this problem, we isolated the world we split the world into two halves. We have the Western Hemisphere and the Eastern Hemisphere. And in the Western Hemisphere, all of the traffic will go to the US, and then in the Eastern Hemisphere, all of the traffic would go to Europe. This, in most situations, this would solve the problem. However, what we found is that because the user sessions are stored in APAC for certain customers, it caused excessive latency to go from APAC to Europe and then back. So even though we were using tools like Amazon Global Accelerator, which I definitely recommend and has done great things for latency. So what we did, we took a step back. We had currently hosted 2 production environments, and we templatized, the same way we templatized the cell deployments, we templatized an entire region deployment, and so that we could launch in APAC, and then all of the rather than splitting the world into two parts, we split the world into three parts, where APAC is serviced locally, the EU is serviced locally, and the US is serviced locally. What this also means, because we templatize all these things and we try to reduce the amount of human labor, it's an investment up front. We wanted to reduce the human labor that it takes to develop these regions. So here's an example of the cell architecture in the US, the cell architecture in Europe, and then the cell architecture in APAC. And when we wanted to set up multi-region recovery, and when we wanted to improve our disaster recovery posture, because we invested upfront in deploying or in templatizing how we could deploy to APAC, we could easily copy and paste to create our failover region. So it commoditizes inherently how your regions are managed. Now, as you grow and as you have multiple regions, one of the issues you run into is keeping everything in sync. How can we be sure that the US region, the EU region, and the APAC region, and the failover regions are all running the same version of the software? So what we do is when there is a new version ready, we use COPF to automatically identify that there's a new version available and create a PR that represents deploying that to the US, to the EU, and to the APAC region. What this means is that human beings no longer have to go through and set everything up manually. They don't have to. It takes out the knowledge needed to deploy to a given region, which inherently is going to eliminate code drift. And the only action from an engineer is to merge the PRs, then monitor the behavior. And if there's any issues, obviously back out the PR and watch everything return to the previous state. Okay, so that part of the presentation is about architecture and how we deploy. Now we're going to switch gears, and we're going to talk about, on the business side, how do you deploy software that is easily consumable by customers? So this is what is business value? Imagine you are building a bridge. Here's a picture of the beautiful Golden Gate Bridge that I found online. And a mission of the bridge is to connect land masses across a body of water. Very, very simple. Everybody understands this inherently. In order to do this, you have multiple different groups that need to participate. You have engineering, you have legal teams, you have to pour the concrete, you have to build the structures, you have to connect the electrical, and then make sure that's all feeding into the main transportation infrastructure, testing, project management, etc. All of these groups have different jobs that they're trying to accomplish that serve the overall mission. And anything that serves that mission can be considered business value. The mission, it isn't over until all of those different departments, until all those different jobs have been completed. So things can go wrong, and then new jobs come up, and then once you solve them, more business value is added. And then 100 years later, we have the bridge that people still drive on. Now, imagine building a merchant. So instead of building a bridge, we are now building an enterprise merchant. Now, the mission is to reach more customers and to sell more goods. Inherently, we know this, but just calling it out. They want to reach more people and sell more things to them. There are still many jobs that need to get done. There are lots of things that need to happen. In this room, we have a lot of the engineers, and then the engineers serve the rest of the organization as they build out their platform, or as they build out their merchant. We have some examples of the jobs that need to be done, or the departments are marketing, payments, the engineering department, and then the compliance department. All of these people need to be successful in order to accomplish the overall mission. Don't worry, there's not going to be a quiz at the end about all the jobs that were on the screen. So here is a simple return on effort calculator. This is a concept that we're going to be using to explain the value of an API. So the jobs that are being done out of that list, you saw roughly, let's say roughly 70 of them. The jobs that are done divided by the amount of effort is the return on effort. So if you have 10 jobs that are done and it takes you 10 sprints to complete them, then you have a return on effort of 1. If you can accomplish those same jobs, 10 jobs to be done to serve the overall organization, and it takes you 5 sprints, then you have doubled your return on effort. An organization will only use a vendor when the return on an effort, which is jobs divided by effort, is greater than building in-house. This is something that, as engineers, we know. If you're looking to accomplish something, you will assess, should I hire this out or should I build it myself? And the way that you just determine to build it yourself is it going to solve more problems if I hire somebody, or is it going to solve more problems if I build it? So VGS, initially, we talked before about the payments architecture, and where VGS is on the, we're on the collect side, and we proxy things in, and then we proxy things out over to the PSPs. We allowed customers to build a compliant and secure environment so that they could share the data with, share the sensitive data with third parties, and then that will enable merchants to move from single processor into multi-processor. So multiple different jobs that are being accomplished. A typical implementation of VGS would have collect, sprint 1, collect the card data, sprint 2, share the data to PSPs, and then monitor. It's typically a two-sprint implementation. What this turns into from an ROE perspective is 3 jobs that are getting done over the course of 2 sprints. So an ROE of 1.5. And this is, if you compare this to the same amount of jobs being done, then those same 3 jobs, if they were to be performed themselves by these merchants, then it would take roughly 6 sprints, which would be an ROE of 0.5. So using VGS in this context had a 3x value to these merchants. It's very easy to understand. So as we were meeting with these merchants, and as we were mostly working with engineering departments, we repeated this over and over using the framework that I showed you before, and that's where we ran into needing cells, and we ran into needing additional regions. But we continued to meet more departments who were also trying to solve problems. So we started out just servicing the engineering department, trying to accomplish their missions, and then we naturally started talking to these other departments. So we had engineering, which led us to compliance, which led us to marketing teams, which led us to payments teams. In each of these departments had more jobs that needed to be done. So from a first look, this is opportunity for an organization. And some of the examples that we started getting, that we were asked to solve were, how can we accept Apple Pay and Google Pay? How can we keep cards up to date? How can we perform network tokenization, which there have been some really great presentations around network tokenization at this conference. And then how can we get enhanced insights into all the cards? These services all make sense. These are real problems that people were trying to solve. And as we developed this, we had our UI data collection tools, and then we had our back-end data sharing tools. Those 2 at the top are what I showed before. And then we added on all of these new products, all these new capabilities. So we had Apple Pay, Google Pay, Network Tokens API, an Account Updater API, an Attributes API to get additional insights. And then where this was the original implementation architecture, where you collect from the client, you share through the backend, it started getting more and more complex on the engineering team. Because you had to integrate Apple Pay, you had to integrate Google Pay, you had to integrate the account updater API, the network tokens API, the card attributes API. And so all these different things, that's additional work that needs to get done by the engineering team. So it's more sprints. Bringing it back to our ROE, it's increasing the amount of effort to accomplish these jobs. So the full implementation timeline, where in the beginning what we reviewed was we would collect the card data and then share the data to PSPs. Then it would turn into sprint 3, okay, now we're going to solve this next problem. Sprint 4, we're going to solve this next problem. Sprint 5, 6, 7, et cetera, et cetera. And so the timeline was growing, it was growing linearly. The more jobs that needed to get solved, the more time it would take. And so what this turned into is an ROE of 1.1. So we started out 1.5. As we solve more jobs, it's actually reducing the return on effort. So the roadblock that we ran into, this is a roadblock talk. How do you ensure fast implementations? What we were finding is that the non-engineering users had to wait for their initial implementation to be completed before the engineering team could start working on their piece of the project. Practically what this means is the engineering team would get their jobs done first, and then after that, we would have then the payments team could get what they need, or the marketing team could get what they need. So we thought to ask the question, how can we increase the return on effort, and compound the value of the engineering time? This goes to what is the design of the implementation, what is the design of the API? In order to understand this, let's talk about how to think about an API. On the left-hand side, we have flexibility, which this is an API that allows you to build anything. It is tool-oriented, and it supports any data formats, and it is built to accomplish engineering goals. These flexible APIs are inherently built to accomplish engineering goals who are then trying to build something else. On the right-hand side, we have prescriptive APIs. And these are APIs that enforce best practices and don't allow you to move outside of the bounds. And it allows people to focus on the core business so that they don't have to think about the engineering work. Now, on the other hand, it doesn't let you focus on anything but the core business, and it doesn't let you focus on the engineering work. Now, typically, these APIs, they align with real-world concepts instead of data structures. And they are built to solve individual jobs. Here's a quick example. What is a credit card using these two APIs as examples? And I'll bring us back to earlier in the conversation when I talked about data tokens versus PSP tokens. So on the left-hand side, this is a collection. A credit card is a collection of data elements. It's a loon-valid 16-digit number and a 3-digit number that cannot be stored persistently. And there's a text field which represents the customer's name, the name on the card. And then it is linked to a 5-digit number or a zip code. On the right-hand side, from a prescriptive point of view, it is a physical object that exists in your wallet. It's provided by a bank or an issuer, and it is the key to an individual's credit account. Obviously, debit cards are tied to the debit account. And it is required to move money into a merchant account. So I give this thing over to a merchant. They can use that to move money into the merchant account. And as part of this, there's opportunity for fraud, which is a business problem. On the left-hand side, the flexible definition is a technical perspective. On the right-hand side, we have a real-world perspective. And from a department standpoint, the left-hand side it focuses on the engineering teams. And then on the right-hand side, we focus on the rest of the business, the departments that the engineering team is building for. And so with VGS, we rethought the API design. I was showing you before, we had the proxies, and then we had all of the different APIs that were available. And so now, on the client side, they send over the data elements, and we have our API that returns business objects. So what this means is we can convert the flexible data elements that are captured by the engineering team and turn them into something that are useful for multiple different departments. On the right-hand side, we have configurable capabilities. So we can still provide back those data tokens that the engineering team can use to accomplish their various goals. And then we can turn on capabilities. So instead of treating everything as a one-off API, we have a consolidated API that can both help the engineering team, and we can turn on features for the rest of the business. This concept can work with any API. So conceptually, we have clients sending over data elements and returning business-level objects. Those business objects can be useful to multiple different departments. And then on the right-hand side, we have multiple different features that are important for, these multiple different features are important for different people in the business. So after we rethought the API design for ROE, remember earlier we had 8 jobs divided by 7 sprints, so we had an ROE of 1.1. Just by changing the way that we thought about the rest of the departments and the rest of or how the data is being used by the rest of the business, and especially in an enterprise, we had those 8 jobs being able to be solved in the same amount of time as originally they were available, because we could turn on functionality. So we can turn on capabilities, and then the customers can be, or the payments team or the marketing team or the compliance team can get what they need. So on one hand, we have flexible APIs. On the other hand, we have prescriptive APIs. And both have value, both have needs, or both have reasons to exist. But when you're selling to an enterprise, that sales cycle may take you 2-3 years in order to get all the way through. And so you want to be able to maximize the amount of value that you can get out of that effort. So an API that does not have business context is flexible, but it will primarily serve the engineering team. And so what you can do when you're selling to enterprises is design your APIs in a way where you spend all the time up front to sell to that enterprise. You go through the compliance rigor with their different procurement teams, and then then you can serve the engineering team, but you also want to be able to service the rest of the departments. And so enterprise-ready APIs, they need to be balanced being flexible and prescriptive. And to accomplish this, an API should offer one interface with many switches behind the scenes to minimize the work for the customer. All right, thank you. Those are all the slides that I have ready. At this point, I will take any questions.
On the VGS itself, do you mostly provide services to merchants, and what kind of services do you also provide to fintechs?
Okay, so the question was, do we mostly supply services to merchants, or do we also supply services to fintechs? And so that's a really good question, because I know a lot of the presentation was specifically about merchants and how they're using it. VGS was actually founded in order to unlock fintechs to be able to quickly become PCI compliant. This was 10 years ago. It was a way to, with that data token capability, especially as the fintech world was coming up. So as you're collecting data, and in the example I showed, it's collecting from an end user, but that could be collecting it from from an issuer, like a Marqeta, something like that. And so as the data is entering your system, because it's configurable based off on the HTTPS protocol, we can say this data element represents the card, this data element represents the CVV, and then you can show that data in an end user app securely in the same way that. So yes, we definitely support fintechs.
And the primary angle would be helping with the PCI DSS compliance. That's kind of your jobs to be done.
Yes, yes. From a fintech perspective, one of the main values is like quickly becoming PCI DSS compliant, and then it's really just reducing. So it's both the compliance side and then the liability side, because then like lots of fintechs they won't want to store things like social security numbers on their servers, or they might want to take a picture of the customer just so that they can share it with some fraud identity provider. All of those things could also be tokenized data. Again, it's very flexible, so any data you don't want to touch can then be shared with a third party. Yeah, good question. Oh yeah. Any other questions? If not, I think we can call it. If there are questions, you guys can catch me after the presentation or in the lobby. And I apparently was talking faster than I expected. I know we're ending a few minutes early, but thank you all for attending.